Hey, calculus fans, let's pick up right where we left off last time. And let's just review the major points. They were very heavy. And for the next week or so, we are going to be using these things almost exclusively. And we are going to be using these facts quite a bit. So, first of all, let's take a look at our final definition of critical number. This is the definition that we're going to settle on, and it will not be revised again. An x value, x equals c, is a critical number of the function f of x exactly when either of the following things happen. Either f prime of c is 0, in which case x equals c is a type A critical number, or f prime of c is undefined, in which case x equals c is a type B critical number. The sign, S-I-G-N, the sign plus or minus of the derivative. If the derivative is positive, then f of x is increasing. If the derivative is negative, then f of x is decreasing. And remember that natural association: positive, increasing, negative, decreasing. And here are some other things related to that. F of x can only change F of x can only change from increasing to decreasing or vice versa at a critical number. If we don't have any critical numbers, the function can't change direction. It's either going to increase or it's going to decrease. F prime of x, the sign plus or minus of the derivative f prime of x. F prime of x can only change sign at a critical number. So if we don't have any critical numbers, the first derivative the derivative can't change from positive to negative or negative to positive. And if the derivative does change sign from positive to negative or negative to positive, we have to have a critical number right there where it changes sign. And then lastly, relative maximums and minimums, the highs and lows on the graph, can only occur at critical numbers. If we don't have any critical numbers, we can't have a relative maximum or a relative minimum. If we do have relative maxes and relative minimums, we have to have a critical number at each one of them. So this is sort of a summary of what we finished up with last time. And I think it's only fitting that we start off with a nice exercise to put all of this stuff to use. All of it. First example. F of x equals 2x cubed plus 3x squared minus 12x plus 5. Determine the intervals on the x-axis over which f of x is increasing or decreasing. And B, identify all relative maximums and relative minimums. That's what we're after. Since we've never done anything like this before, I guess the first thing we have to figure out is, what do we do? What do we need to do? What should our first step be? Now, we're going to be looking for intervals over which f of x is increasing and decreasing. And what do we know about increasing and decreasing functions? A function's increasing exactly when what? The derivative is positive, right? And the function's decreasing exactly when what? The function is decreasing exactly when what? The derivative is negative. So the sign of the derivative, plus or minus, tells us where the original function f of x is increasing or decreasing. And relative maximums and relative minimums, what do we know about them? They can only occur where? At a critical number. And how do we find a critical number? A critical number is where the derivative is 0 or where the derivative is undefined. So we need the derivative to find out where f of x is increasing or decreasing, because the sign of the derivative tells us where f of x is increasing and where it's decreasing. And we need the derivative to find our relative maximums and relative minimums, because these only happen at critical numbers, and we find our critical numbers from the derivative. So without a doubt, the first step has to be compute the derivative and find the critical numbers. F prime of x is 6x squared plus 6x minus 12. So we have the derivative. Now we have to find the critical numbers. There are two kinds of critical numbers, type A and type B, and we have to think about this. What is the identifying characteristic of a type A critical number? If we have a type A critical number, then the derivative is 0 at that value of x, right? So the derivative is 0. To find the critical number, we set the derivative equal to 0, and we see what that forces x to be. I look at the left side and I have a common factor. Every term has a factor of 6. So I'm going to divide both sides by 6. So let's see, how does that factor? Ooh, I wish you were here in person, you could help me with this. I guess it's x plus something times x minus something. Yeah, I think, what? X plus 2, x minus 1, is that it? Plus 2x minus 1x is x. Yep, that's it. Okay. So we have two type A critical numbers, x equal -2 and x equal 1. I've taken care of my type A critical numbers. I need to look for type B critical numbers also. And let me ask you something. What is the identifying characteristic of a type B critical number? A type B critical number, that's where the derivative is undefined, right? So we're looking for values of x such that the derivative is undefined. And usually when an expression is undefined in mathematics, not always, but usually when an expression is undefined, it's because we've divided by 0. And most of the time when we're looking for a type B critical number, we're looking for an x value that causes division by 0. So let's take a close look at our derivative. Here it is. What value of x causes us to divide by 0? Well, here's the derivative. The derivative is 6 times x squared plus 6 times x minus 12. I don't see any division going on here at all. We have multiplication, we have addition, we have subtraction, we have exponentiation. We're not dividing by anything anywhere there. So there's no way that we can be dividing by 0. So in this particular example, we don't have any critical numbers. No type B critical numbers. We do have type A, -2 and +1. So I'm going to make a record of this. Write down the results before I erase the board completely so I don't forget what we just did. Okay. There. Now if I erase the board, I won't have lost too much information. Draw a sine graph of the derivative. And we use the critical numbers to partition the x-axis. A sine graph, that's just a picture of the x-axis. And in that picture of the x-axis, we stipulate where the derivative is positive and where it's negative. And very closely related to step 2 is step 3. In each interval, and I will say this, the critical numbers partition the x-axis into subintervals. So in each of these subintervals, we choose a test value. to plug into the derivative. So here's my sine graph of f prime of x and I have two critical numbers, x equal -2 and x equal 1. So I've used my critical numbers to partition the x-axis into subintervals. And for step 3, in each of these intervals, I choose a test value to plug into the derivative. I'll start here first. I have to pick some number between -2 and +1 to plug into the derivative. And it should be something that's easy to compute with. Now in this interval I have -1, I have 0, whole numbers. Both of them are good candidates. 0 is an especially good test value because it's easy to plug 0 into a function and compute the result. So I'll take my test value and plug it into the derivative. And when I plug 0 into the derivative, I get -12. So right here, when x equals 0, the derivative is negative. Now, I don't know why, I have this crazy hunch that because the sign of the derivative is negative right here at x equals 0, the sign of the derivative is probably going to be negative throughout this whole subinterval. I'm not really sure why I feel that way, but maybe I shouldn't assume that this is true. But I have a feeling that if the derivative is negative right here at x equals 0, then the derivative is probably negative for every value, every x value in this interval. I'm not sure why I feel that way, but I do have that hunch. Now over here, I'll pick a test value. And 2, 3, 4, 5, they're all good test values. So I'll pick 2. That's a good value. And I'll plug it into the derivative. 2 squared is 4 times 6 is 24. Plus 12 is 36, minus 12 is 24. When x equals 2, the derivative is positive 24. And I don't really care about the 24 part so much. All I really care about is that when x equals 2, the derivative is positive. So I'm thinking that since the derivative is positive when x equals 2, the derivative is probably positive throughout this whole interval. I'm not sure why I can justify that, but I do have this hunch. And I hope I don't end up regretting making that assumption, but something tells me, and I hope I'm right, that because the derivative is positive when x equals 2, it's going to be positive throughout this whole subinterval. Last but not least, I will pick a test value over here, and I'll pick -3. And why I picked -3? Well, it's a whole number and it's over here. I plug in -3, -3 squared is 9, times 6 is 54. 6 times -3 is negative 18. So I have 54 minus 18 is 36, minus 12 is 24. So when x is negative 3, the derivative is positive 24. And again, I don't care about the 24 part too much. What I really care about is the fact that when x is negative 3, the derivative is positive. And call me crazy. You won't be the first to call me that. But I just have this hunch that if the derivative is positive, right here at x equal negative 3, then it should be positive throughout the rest of the interval. And I can't really explain why I feel that way, but I guess I better make sure I'm right before I go too far. When x is 2, the derivative is positive, and I just have this feeling that throughout this interval, we keep going this way, the derivative is going to stay positive. It's going to be positive for every value of x in this interval. And I guess the proper question to ask would be this: how do I know that maybe somewhere out here, at when x is 1,000,000 or 2,000,000,000 or something, the sign of the derivative doesn't change from positive to negative? Just because the derivative is positive here at x equal 2, how do I know that as I move out here, the derivative might not change sign and become negative? How do I know that that can't happen? What do you think? And help me out, please, here. Don't let me make a fool of myself. And I think some of you have figured it out. The derivative is positive when x equals 2. And we can't have any value of x out here where the derivative becomes negative. Why? Because the only place where a derivative can change sign is where? At the critical numbers. And guess what? These are the only critical numbers that there are. These are the only two places where the derivative can change sign. So the derivative can't change sign out here from positive to negative because there are no critical numbers out here. These are the only two critical numbers, and besides these two, there are no more. So these are the only two critical numbers. Excuse me for a minute. Well, that was nice. Some little nasty little note from Microsoft saying I have to log into my account right in the middle of me making a video, and to that I say thank you very much, Microsoft. Okay. Now, maybe I am crazy, but I was right here. The derivative was positive at x equal 2, and based on that I concluded that the derivative has to be positive throughout this interval. And it turned out I was right. The derivative can't change sign in this interval because there are no critical numbers here. And I may be crazy, but I concluded that because the derivative was negative when x is 0, the derivative had to be negative throughout this entire interval. And I was right. The derivative can't change sign in this interval because between negative 2 and positive 1, there are no critical numbers. So there's no place where the derivative can change sign in this interval. And similarly, I was right in concluding that because the derivative is positive when x equals negative 3, the derivative has to be positive throughout this entire interval. So, steps 2 and steps 3, done. And it turns out that I've answered half of what I've been told to find. Whoops. I now know where f of x is increasing, because I know that wherever the derivative is positive, f of x, the original function, has to be increasing. And on this interval on the x-axis from negative infinity to negative 2, the derivative is positive. So from negative infinity to negative 2 on the x-axis, f of x is increasing. And f of x is increasing on this interval too, because the derivative is positive here. From x equal 1 all the way to infinity, f of x is increasing on that interval. So on the interval from x equal 1 to infinity, f of x is increasing. And I'm going to write down how it is I know that. F of x is positive on these intervals. F of x is increasing on these intervals because the derivative is positive. And we know that those two things go together. Now, decreasing. F of x is decreasing on the interval or intervals f of x is decreasing on this interval on the x-axis from negative 2 to positive 1. And how do I know that? Because between x equal negative 2 and positive 1, the derivative is negative. And this is the only interval over the x-axis for which the derivative is negative. So I'll write that information down, and I'll give my explanation. I know that f of x is decreasing because on that interval, the derivative is negative. So I've answered half of what I've been asked to find. The only thing that I don't know is the relative maximums and relative minimums. So I'll write down step 4 here. Step 4, define the relative maximums and relative minimums. Sketch a rough graph of f of x. Now remember when we were doing asymptotes, I said we've progressed a little bit since the times when we'd always draw the x and y axes when we graph a function. When we were doing asymptotes, we realized that the asymptotes were places on the graph of the function where important features occurred. So we used the asymptotes as our vertical and horizontal references, not necessarily the x and y axis. Similarly, now that we know some calculus and we know something about increasing and decreasing functions, we don't necessarily restrict ourselves to using the x and y axis for frames of reference, because the important features of the graph of the function may not occur anywhere near the origin. So let's see, what is happening? Well, we have critical numbers, and at those critical numbers, the graph changes from increasing to decreasing and from decreasing to increasing, and that's pretty important. So what I propose here is that we use the critical numbers as our frames of reference. So here is our first critical number, x equal -2. And here's our second critical number, x equal 1. And are we getting that on the screen? Yes, we are. Very good. Okay. Now, over here to the left of x equal -2, from -infinity to -2 on the x-axis, what's f of x doing? Isn't it true that from -infinity to -2 on the x-axis, right over here, f of x is increasing? And what does an increasing function look like? Goes uphill from left to right, doesn't it? So that's what I'm going to draw. Here's my function going uphill from left to right. So here's f of x increasing. F of x equals 2x cubed plus 3x squared minus 12x plus 5. So over here, f of x is increasing. Now, what about here, between here and here, between x equal -2 and x equal 1? What's f of x doing? Isn't f of x decreasing between -2 and +1 on the x-axis? And what does a decreasing function look like? It goes downhill, doesn't it? So here's my function decreasing, going downhill. And I'll write decreasing. And now over here, for x greater than 1, from x equal 1 to x equal infinity, what's my function doing? It's increasing again, isn't it? And an increasing function goes uphill. So here's my function increasing. Now, I'm supposed to be looking for relative maximums and relative minimums. How does this help? Well, relative maximums and relative minimums are the high and low points on the graph, right? I wonder where that is. Oh my goodness. Here's a high point on the graph. This is a relative max. And this is x equal -2. And the y coordinate of this point, let's see. This is the graph of f of x, right? So the y coordinate of this point is f of x evaluated at -2, and I'll write f of -2. So that's my relative max. Oh, here's a low point on the graph, no doubt about it. This is a relative min. A relative minimum at x equal 1. And to get the y coordinate of this point, I take x and plug it into f of x. So the y coordinate is f evaluated at 1. Now, I just need to summarize that. But it's interesting how we found our relative maxes and mins, right? Just use the information about increasing and decreasing and sketch a rough graph of f of x. And then just stand back and look at the graph and say, oh, here's a high point, must be a relative maximum. Oh, here's a low point, must be a relative minimum. And that's exactly the way it works. So, let me write down my information. Relative max, -2 f evaluated at -2. And technically, I am obligated to compute the y coordinate of this point, so I'll do that. If I plug -2 in here, that's -8 times 2 is -16. -2 squared is 4 times 3 is +12. -2 times -12 is +24. +5, so let's see. I have 12 plus 24 is 36, and then 41. -16, I guess that's what, 25 maybe? So -2, +25, that's my relative max. And my relative min, good gravy, I almost erased it. 1, and f evaluated at 1. And to get the y coordinate, I just take the x coordinate and plug into f of x. So I have 2 plus 3 minus 12 plus 5. 5 plus 5 is 10 minus 12 is -2. That's my relative minimum. And I am so satisfied with these results that I'm going to take my answers and I am going to encapsulate them in this box, just so that I will know that, yes, these are the answers that I was asked to find. And let me write, whoops. Yeah, I guess I'm supposed to encapsulate all of the answers, aren't I? Okay. And I do have a comment about this. The process that we use to determine where f of x is increasing, decreasing, and to find the relative maxes and mins It's called the first derivative test. So when our authors ask us to determine where f of x is increasing and decreasing using the first derivative test, that's the process that we just used. When the author asks us to find the maximums and minimums, the relative maximums and relative minimums, we use using the first derivative test. That's the process that we just used. And I'm going to check and see if they have any other funny little terms. Let's see. Applying the first derivative test. Yes. One more comment about our author's terminology. For those of us who didn't take Latin in high school, and those of us who took it, but it's been 50 years and we don't remember a single thing, relative extrema, that's what our authors mean. That's what our authors are referring to when they say, or when they want us to find relative maximums and relative minimums. When they ask us to find the relative extrema, they're telling us to find the relative maximums and the relative minimums. Now, why they can't say relative maximums and relative minimums, I don't know. But two things. The process that we use to determine where the function f of x is increasing and decreasing and where the relative maximums and minimums were, that process is called the first derivative test. That's what we just did in this example. And also, when the authors refer to something as relative extrema, or they tell us to find relative extrema, they're telling us to find the relative maximums and the relative minimums. Well, that exercise turned out so well, I'd kind of like to do another one. Okay, here's another good one. F of x is 4x cubed minus 15x squared minus 18x plus 8. Determine the intervals on the x-axis over which f of x is increasing and f of x is decreasing. Identify all relative maximums and relative minimums. First step, what is it? Compute the derivative, right? Because that tells us increasing and decreasing for f of x, and that's also where we get our critical numbers. You know, there used to be an E in the word compute. Okay, there's our derivative. And now we need to find our critical numbers. Type A critical numbers. What is the identifying characteristic of a type A critical number? That's a value of x that makes the derivative 0, right? Okay. So f prime of c is 0. And we set f prime of x to 0 and solve for x. So we set the derivative equal to 0. And that means that we have 12x squared minus 30x minus 18 equals 0. And you know, these are pretty big numbers. Not all of them have a factor of 12, but all of them do have a factor of 6. So I'm going to divide both sides by 6. And hopefully I've done that right. Divide by 6, divide by 6, divide by 6. I think I'm good. Okay. Now we got to factor this thing. 2x plus or minus something, x plus or minus something equals 0. And I'll tell you what, remember a few weeks ago we said that if we could find a number to plug into a polynomial and that number makes the polynomial 0, then x minus that number is a factor. And the best place to look for those factors are the whole number factors of the constant term. So let's see, 1's a factor, I'll plug that in. And if I plug in 1, I get 2 minus 5 is negative 3 minus negative 3, 0. No, that's not going to work. Plug in 1, positive 1. I get 2 minus 5 is negative 3. No, I tried that. Negative 1, negative 1. Negative 1 squared is positive 1 times 2 is 2. Minus a negative 5x is plus 5. No, that's not going to work either. Okay, well, let's try 3 and negative 3. Plug in 3, we get 9 times 2 is 18. Minus 15 is 3, minus 3 is 0. Beautiful. When we plug in x equal 3, we get 0. So that means that x minus 3 is a factor. X minus the number that we plugged in to get 0 is a factor. And we can figure the rest out. We multiply this out, and that's got to give us 2x squared minus 5x minus 3. So whatever goes here has to multiply by minus 3 to give us minus 3. Let's see, what could that be? I'm guessing plus 1. Now, if we do that, does that also give us negative 5x? Let's see. Plus x minus 6x is negative 5x. We did it right. Beautiful. So that means 2x plus 1 equals 0, which means 2x equals negative 1, which means x equals negative 1/2. That's a critical number. And x minus 3 is 0. That means that x equals 3 is a critical number. type A critical numbers. Now we have to look for type B critical numbers. And what's the identifying characteristic of a type B critical number? Isn't that a value of x that makes the derivative undefined? And typically when we're looking for a value of x to make the derivative undefined, we're looking for a value of x that makes the derivative 0. So we're looking for an x value, we're looking for a value of x that causes us to divide by 0 in the derivative. So let's see, how can that happen? We have 12 times x squared minus 30 times x minus 18. We've got multiplication, we've got exponentiation, we've got subtraction. There's no division going on anywhere. So it's not possible to divide by 0 here. We're not going to get any type B critical numbers here either. So we have no type B critical numbers. Wow, you'd think sooner or later we'd run into some, wouldn't you? We will. Now, let me write down my results. Critical numbers, and that's x equals -1/2 and x equals 3. And I guess up here, not for permanent storage, but temporary storage, I'll write down that my derivative is 12x squared minus 30x minus 18. Okay. I can erase everything else. And step 2, what was that? Draw a sine graph of the derivative using the critical numbers to partition the x-axis. Okay. And along with that, in each subinterval or each interval, pick a test value to plug into the derivative. Here's my x-axis, my critical numbers, x equals -1/2, and x equals 3. Okay. And in each interval, we'll pick a test value to plug into the derivative. We have 0 in this interval, and 0 is always a great test value. If we can get it, it's a great test value. So I plug 0 into the derivative, I get -18. And what really interests me is not the 18, but the negative. When x is 0, the derivative is negative. And from our last example, we know that the sign of the derivative at any point in this interval determines the sign of the derivative at every point in this interval. So the derivative is negative in this interval. And I will write down f prime of x less than 0. Yeah, as a matter of fact, maybe I'll do it this way. Okay. Now, test point over here. Well, pick a whole number for sure, and 4 is good. And by the way, believe it or not, the number 10 is also a good test point. Think about it. 10 is an easy number to square. We get 100. And then it's easy to multiply by the coefficient. So 10 is oftentimes a good test value also. Now 4, we plug that into the derivative. 12 times 6, you know what? 12 times 16, I don't know what that is. I'm going to hit the chicken switch and I'm going to go for 10 as a test value. 10 squared is 100, times 12 is 1200, minus 300 is 900, minus 18 is 882. The 882 isn't really all that important, but the fact that when I plug in 10, I get positive 882, that's the important thing, the fact that it's positive. So I will record the sign of the derivative, and underneath I'll write f prime of x greater than 0. Excellent, excellent, excellent. And, what the heck? I'm on a roll. Let's pick negative 10 as a test value. Negative 10 is an easy number to square too. Negative 10 squared is 100 times 12 is 1200. Plus 300 is 1500. Minus 18 is 1482. Now the 1482 isn't all that important, but the fact that it's a positive 1482, that's what I want to take notice of. When x is negative 10, the derivative is positive, and that's the important thing. The sign plus or minus of the derivative. So I'm going to write underneath that f prime of x greater than 0. Oh man, we are rolling. We are rolling. And we have enough information right now to answer half of what we've been asked to find. F of x is concave up. No, I'm sorry. Forget I said that. F of x is increasing on the intervals well, let's see. The derivative is positive here, so f of x has to be increasing from negative infinity all the way to negative 1/2 on the x-axis. And the derivative is positive here too. So f of x is increasing on this interval for x equal 3 to infinity. And I'm going to write down here how I know this. I'm going to write because f prime of x is positive. And we remember that. Positive derivative increasing function. Oh, decreasing? That's where the derivative is negative. And it's negative between x equal negative 1/2 and x equal 3. And this is the only interval where the function's decreasing. So I write down f of x is decreasing on the interval or intervals x equal -1/2 to x equal 3. So just like that, we've got half of the exercise whipped. And believe it or not, this was the hard part. It's all downhill from here. All I have to do now is find my relative maximums and relative minimums. And do you remember how it is that we do that? To find relative maximums and relative mins, sketch a rough graph of f of x using the information that we've already accumulated. So over here, I'm going to write f of x equals 4x cubed minus 15x squared minus 18x plus 8. And again, I'm not going to use the x and y axes as my frames of reference. I'm going to use my critical numbers because that's where all the interesting things happen. The asymptotes and the critical numbers. And my critical numbers, x equals -1/2. So this is the vertical line. X equals -1/2. And x equals 3. Here's the vertical line. X equals 3. Over here to the left of x equal -1/2. To the left of x equal -1/2. From -infinity to x equal -1/2. What's f of x doing? It's increasing, isn't it? And what does an increasing function look like? It goes uphill, right? It goes uphill from left to right. So here's f of x going uphill, and I'll write increasing here. Now, between x equal -1/2 and x equal +3, what's f of x doing? It's decreasing. And what does a decreasing function look like? It goes downhill from left to right, doesn't it? So here's our function, our graph, going downhill from left to right. The function's decreasing. And then I just ask myself, what is f of x doing over here to the right of x equal 3? From x equal 3 to x equal infinity, oh, f of x is increasing again, isn't it? So the graph goes back uphill. Here's f of x increasing. And then I just look at my graph, and the relative maxes and mins jump out at me. Here's a high point. Well, son of a gun, this has to be a relative max. X equals -1/2, and the y coordinate is f evaluated at x equal -1/2. That's a relative max. And here's a relative min. It has to be relative min. And at this point, x is equal to 3. And the y coordinate is f evaluated at 3. Now all I have to do is formalize this. I'll put this in my box of answers, and I am done. So let's see, what did we find out? Relative max, -0.5, and F evaluated at -0.5. And I'm obligated to compute what this is. Oh, let's say 4x. If I have -0.5 and I cube it, let's see, that's -1/8, isn't it? Times 4 is -0.5. If I have -0.5 and I square it, that's -1/4. Times -15 is +15/4. -0.5 times -18, that's +9, I hope, plus 8. Well, let's see, this is -2/4, isn't it? Plus 15/4 is 13/4. And 9 plus 8 is 17. My goodness. Is that really what I want for an answer? I don't think so. I beg your pardon. Please excuse me for being a moron. -0.5 squared is +1/4. Times -15 is -15/4. Okay. I think I'm looking a little bit better now. Maybe. I'm still not sure I like this. Oh well, we'll go for it. This is -17/4. And this is +17. Let's see, 68 minus 17 is 41. Okay. Somehow I doubt the accuracy of this answer, but it doesn't look like I'm going to get anything else. So there's our relative max. And relative min. That's 3f of 3. And I'm obligated to compute that y value also. So 3 cubed is 27 times 4 is 108. 3 squared is 9 times 15. Good golly, what is that? 135 maybe? Let's see, 10 is, yeah, it's 135. Okay. And 3 times -18, 54, plus 8. Okay, so let's see. -135, 185, 189. So it looks like we're looking at -73. Okay, those are my answers, and I'm sticking with them. And again, we used the first derivative test to find out where the function was increasing and decreasing, and to find our relative maximum and relative minimum. And that's going to be our bread and butter, or our button breader, whatever it is. Whatever it is, that's what we're going to use, the first derivative test.